Welcome to Data Science in Python. This time we're going to be assessing the residual normality, or the normality of the residuals from your ANOVA. Notice all of the items that I need up here to make this work. So we're building up this sort of library. There's ways you can pull out individual functions, but we're not going to worry about that right now. Specifically what I added, again, from when we added or checked normality in regression, we use SciPy stats. I've called it ST this time, and we need the stats model API as well in order to get a QQ plot if we want that. We're looking at the fructose dataset, and if you don't have the fructose dataset, you should probably go back and look at the last couple videos so you can see where we're at, because a lot of this is condensed from what I did last time and the time before that. So we have some data, and we're looking to see whether there are differences crossed here. We did an ANOVA. We found there were differences. We did a Tukey's HSD, and we found that this one is different than the others. But how reliable are our inferences? Because they do depend on the notion of the residuals being normally distributed. So I'm going to run through this real quick. Let's just run this total bit here. You might want to pause this and make sure you have all of these packages available and typed in. Okay, so that ran. We read in the data. Here I'm going to run the ANOVA. Just so we've run it again. The code is here. There's the ANOVA table. Okay, so just like when we were doing linear regression, we have FR1 underscore LM. That's the name of our linear model in this case that does the ANOVA. Okay, so and dot resid gives me the residuals. We're going to fit to make sure that the variances match up. I'm going to put a line at 45. So I'm going to check the normality this way. And here's my picture. And it seems to follow a straight line fairly well. So from this, you would say, oh, yes, it is definitely normally distributed, and everything's good. You can't say that because this isn't a test. It's an assessment. It's a tool to look at it and go, well, maybe it is, maybe it isn't. But in reality, it's not a test, and you actually want to check the Shapiro-Wilks test. And I just already put this in here. This is the code we're going to use to do that. It's exactly the same as what we did last time, except I've named the SciPy stats as ST. However, I'm not going to just run this directly, okay, because it's a hypothesis test. And you're like, oh, no, Ed, not again. But I'm trying to be a good statistician and show you that this is a hypothesis test. It has a null hypothesis that the residuals are normally distributed. Against HA, the residuals are not normally distributed. Our significance level. Remember, I don't want to reject here. I want there to be a lot of evidence to show me that, look, this thing's really not normal before I declare it not normal, because my life changes. I'm going to have to go back and analyze the data in a completely different way, and I don't want to do that. I want things to be easy for myself, so don't go overboard here. So you want to make it hard to reject, so you choose a small alpha. Let's see, we have a significance level, then we need a decision rule. And that says if the p-value is less than alpha, we reject H naught, and then we're going to need a test statistic, which should have been above it, but we're just going to use the ST Shapiro from SciPy.stats. Everybody should know what that means. I don't have to put ST Shapiro. I should just put Shapiro because that's my alias. But it tells you exactly how you did it. You went and used in Python this package and this function. So anybody who reproduces this should get exactly the same result as you. And this is good documentation. All right, so if I run this real quick, I can get the p-value. And here we go. And the second one is the p-value. And I'm just going to copy reasonably far out. And then say the p-value is this. I have it, and then I can make my decision. Since the p-value is equal to this, which is clearly greater than my 0.001, which is equal to alpha, we fail to reject H naught. Hooray! That means my life doesn't have to become complicated. Conclusion. We have insufficient evidence to claim that the residuals from our ANOVA are not normally distributed. All right, so that's it. Okay, so in the next one, we're going to look to see what about constant variance. So I will see you there.